we've talked about the potential for cloud, opportunity for cloud, the challenges with running applications in the cloud. And in this lecture, we'll talk about another complementary problem, and that is how do you deal with large-scale data? How do you process it, analyze it? What are the various key challenges around that? And how do you combine these two? How can big data problems be solved using cloud computing, and how platforms such as Apache Spark, we'll talk about today, are sort of the glue between your application. How do you design distributed applications in order to use distributed systems, right? So they sort of fall in between. So in a sense, today's talk will be at the platform as a service layer, if you guys remember the first day and the subsequent lectures, and how can these platforms as a service make use of the infrastructure as a service available in the cloud, okay? All right, so again, these slides are from a variety of resources, so these are available over here, so you can go later on and have a more detailed look at some of these sources if you want to get much more information than what I cover in today's lecture. With the question of what is big data and where does it come from, right? How many of you have heard the term big data? Right? So pretty much everyone in the room, right? If you haven't, you've been living under a rock for the last decade or so, right? So if cloud computing was a hype maybe 10 years back, big data was the hype 5 years back, and ML and AI is the hype today, right? And who knows what's going to be in 5 years' time, right? So big data has a variety of descriptions, definitions, characterizations, and so on. So just to sort of give you a sense of what people thought about big data, this is about 5 years back, at the hype of the peak of the hype around big data, right? So folks at Berkeley just went out, did a survey of various thought leaders in technology and asked them to sort of describe what they thought big data was. And they did a word cloud out of that, right? And you'll see some various keywords pop out amongst that. So big data is large, it's complex, it's got a lot of volume, there's a world over there. I don't know what world means over there. Maybe it's worldwide data from everywhere. You want to do analysis on top of that. It has different technologies that are available, and so on and so forth, right? So point being that big data back then and even still today has a bit of a fuzzy nature to the terminology itself. Just as maybe a week back when you started off, clouds and hybrid clouds were a fuzzy concept, right? If someone asked you what was cloud computing maybe a week back, you'd have given them some reasonable answer, but now you can actually be much more precise, hopefully. Can you guys define cloud computing and the various characteristics if someone asked you? You can, right? Anyone still not sure? Good, right? So it's sort of like that. So big data is like how you thought about cloud computing a week back, but once you start working with it, then you start realizing that, hey, there are specific dimensions to big data. If it has certain properties, then it's possible that it's big data, right? So just to sort of give you a flavor of what some of these definitions were or descriptions were from various people from whom this was solicited. Some talk about big data as the philosophy of collecting data now and figure out what you want to do with it later, right? And that is more like an opportunistic view of big data, right? So it's almost like saying, hey, today I have the chance to maybe eat pizza, right? And let me hog, right? Let me eat all the pizza, let me put some in my bag, and let me take it and put it in the refrigerator. So it's sort of like that kind of a mentality. If I can store it when I have access to it, right? Let me keep it and then figure out what I want to do with it. Maybe I go give it to my friends, maybe I have do something else with it later on. So that's one view, which means that you don't need to necessarily collect it with a specific purpose in mind. You collect it because you can collect it, right? And because you can store it, right? Not necessarily because you need it right now, right today, right? But maybe a week from now, a month from now, a year from now, it might be gold mine if you have collected enough data and you want to sort of pull out interesting insights out of that, right? Another view is something where your standard methods and standard data systems cannot easily process the data or solve the problem that you want to do using that data, right? Let's say someone gives you a large text corpus, right? So let's say all the English novels in the world were given to you, and they said that, hey, find out which are very frequent words that come out of that, right? So maybe you can put it in a relational databases and start querying or doing aggregates and joins out of that. Maybe you can write a bunch of bash scripts that do sed, awk, and all those things, sort, and so on, and word count to get an answer out of that. Maybe you can write a C++ or Java program or a Python program to solve that, right? But the point being that as the size of the data grows, each of these techniques that you might be familiar with start breaking down, right? So they don't scale, or they don't have the right set of primitives that you want, right? So that's one of the views of big data, in the sense that the techniques that you currently have are inadequate to process the data. Another view is where data is really messy, which is another way of talking about unstructured data, semi-structured data. And sometimes you don't even know what questions to ask from the data, right? You have it, you sort of have a sense of what you could answer, but you don't know exactly how best to describe it, or even how best to ask for it, right? And this typically happens if you have planned your data organization. If you have a nice ER diagram, you have a nice schema, you have nice data ownership, you have a nice pipeline that brings in your data from maybe your field offices to your central office and so on. That's very well structured, and you actually collect data with a clear intent in mind, right? So maybe you want to have a forecast of your sales over the next 1 year, right? Or you want to sort of you want to collect some data sets in terms of your number of employees that you have, so that you can plan your hiring, right? So these are all very structured information that enterprises know you need ahead of time. But then you might have a big glob of data. Maybe you are running a online website for an enterprise, and you have a bunch of comments that people have left, right? Now, how do you go and sort of deal with potentially tens of thousands of these comments and try to make sense out of that without having someone manually go and look through all of that, right? So that's where some of these challenges come in as well. And lastly, sort of some people, again, 5 years back, who knows what was going through their mind, they think of big data as a cultural movement by which you continue to discover how humanity interacts, right? That's a very as fuzzy as it gets in terms of how you describe data, right? It's almost like if you're one of those, what do you call that? If you're in some beauty pageant, then they ask you a question, right? It's almost like saying that I'll get world peace kind of answer over here that's going on, right? But one description that I prefer, right, is talking about big data as something which has characteristics that exceed the capability of current generation of algorithms, systems, and techniques, right? So, so it has both to do with the methods or algorithms that you might have. For example, if you want to do some kind of a graph traversal, right? Maybe your Dijkstra's BFS or DFS would work on a single machine, but if the graph is too large, it's not going to sort of be good enough, right? So you have to come up with new algorithms, maybe distributed algorithms, maybe approximate algorithms, and so on, where you have to scale to large data sets. Likewise, you need systems that can deal with such large data. Maybe the entire graph doesn't fit in memory of a single machine, right? You're forced to sort of put it on different machines, or you're forced to keep it on disk and in memory and dynamically move data from disk to memory and so on, right? So there are different methods that you might have to think about to deal with such data, and different systems that you might have to design and develop, right? Both software systems as well as hardware systems, in order to address these challenges, right? And the whole idea is to sort of get some useful value out of such big data, right? And since all of you have heard of big data, you probably know where big data comes from as well. And one of the most common sources of big data, as we all know, is from the web, right? So web is probably the largest open data that's out there. If you wanted to, you could go and sort of start downloading terabytes of data just by crawling websites. So go to one web page, look at all its links, go to those web pages, download it, look at all their links, go to those web pages, and so on. So you could literally start a breadth-first traversal through the entire World Wide Web, correct? You guys could write a program, right? So just do a couple of wgets or whatever it is, and you could literally be writing your own web crawl, and within a few days or weeks, you could have potentially downloaded the entire World Wide Web onto a single machine if you have enough disk and bandwidth storage, right? And as we know, the web has been around for a couple of decades now, and it's been growing. So the y-axis over here is actually in log scale, which means that if the plot is rising linearly, effectively it's an exponential growth. And it's starting to sort of plateau out in the last decade or so in web pages out there, right? And that's a lot of data. And if you look at websites like Google, where you do your search and so on, they are crawling this entire web on literally a daily basis, right, or a weekly basis, so that if a new website pops up or the content of a website changes, they have the latest data available in order to perform your searches and so on. And you also have not just the number of web pages that are growing, but also the complexity of web pages are growing as well, right? So how many of you have looked at a website from maybe 20 years back? Did people have websites 20 years back? They did, right? So, and if you look at the web page, it's going to be very, very plain, right? It's almost like it's like a console shell, right? There's a difference between your like your window manager or your GNOME or Windows interface versus a bash shell, right? So the web page looks very sparse. And more often than not, those web pages are literally typed by hand, right? Nowadays, very few people actually edit an HTML web page by hand. You also have your all fancy sort of composition interfaces that sort of create those web pages for you, right? And a typical web page nowadays, if you look at the source, it'll run into probably several kilobytes in size, right? Well, some of these old websites, it's probably the whole thing will fit within 20 or 30 lines, right? And that's the entire website, right? So the content, both in terms of the number of objects that you might have, media and various types of other objects, as well as the size, absolute size of the web pages themselves have been growing dramatically. And this means there's more data moving around, more data to index, more data to search over and so on, and crawl over. So that's another challenge when you start talking about analyzing such data. You also have the growth of mobile platforms. So mobile platforms are not just consumers of data, but you're also producers of data, right? So any app that you have is very likely generating a lot of background data that it's sending back to its app developer sitting in the cloud most often than not, so that they get a sense for how you're using their app and how how frequently you're on the phone, or maybe how many friends you have and so on. There's a lot of background data that gets collected, background telemetry that gets collected. So you're both consuming data as well as producing data just by interacting with your smartphone, right? And obviously, social network is another big source of online data. So the number of users of various microblogging sites, Facebook has been growing phenomenally. It's almost linear, and probably 1 in 3 people in the world probably have a Facebook account, right? And likewise over here as well, it's not just the Facebook website, but most people nowadays go to Facebook on their mobile phone app, right? So that's been growing as well. And here it's much more dynamic content. It's not like a more or less static web page that you go and browse. It's live interaction that you have with your friends and your relatives and so on. And there's a lot more richer content that's happening. And you also have the relationship amongst various people. You're a friend of someone. So there's a lot of analysis that goes on that Facebook does to recommend friends to you, or recommend news articles to you, and potentially recommend products to you as well as part of their advertising campaigns, right? So there's a lot of analysis that happens on top of the content that you generate and post on Facebook, and the interactions that you have with others on Facebook, right? That's a big gold mine of data for Facebook to analyze, and that's where some of these big data platforms come into play as well. The other big source of data is again of unstructured data is video, whether it's YouTube or Netflix or Amazon Prime or Hotstar or whatever is your favorite medium for consuming content, right? So that's a lot of high bandwidth data that gets moved around on the internet. In fact, a majority of or a large chunk of the internet traffic is just video content that people are consuming, right? And on top of that, when you talk about unstructured data, it's not just video, but nowadays it's also audio, right? Pretty much all of you have a smartphone which has Siri or Cortana or Alexa or one of these assistants that are listening to what you're talking about and listening for commands. But the key point is that it's listening, it's processing the audio literally on a continuous basis. And sometimes it's done locally on your smartphone, sometimes it's actually sent in the background to the cloud where such data is processed. So this again is a lot of large size data as well as unstructured data, right? Because if you're effectively processing signals, not just text. And science, so we've talked about web, we've talked about mobile and social media and so on as sources of big data. But interestingly, scientific disciplines are also major producers and consumers of big data. In fact, the last couple of years, you've had various breakthroughs happen in terms of discovery in particle physics, like the Higgs boson, the God particle, if you guys have heard of that. All of that was thanks to analyzing a lot of data that gets collected from these large-scale scientific instruments. The Large Hadron Collider that's in the boundary between France and Switzerland, that's actually a huge circle. It's several kilometers in diameter, and all it does is essentially sort of send these particles around in a circle and keeps accelerating. It's like sort of if you sort of hung a stone on a piece of thread and you kept spinning it, right? As you keep spinning it, you can keep increasing the speed, right? That's pretty much what happens in these particle accelerators. They sort of send a circle through, like a particle through in that big, huge, gigantic loop, and it keeps accelerating and accelerating and accelerating to speeds that approach the speed of light, and then they essentially have these particles collide with each other. And when you collide with each other at close to the speed of light, they actually break apart your atomic bonds and so on, and they become constituent pieces, right? And this is actually collected. They have some really high fidelity instruments that can measure subatomic particles, and you'll have billions of these particles that are generated for each of these collisions, right? And by studying these subatomic particles, that's by studying the properties of them that's measured as part of these instruments, you can actually figure out if all the theoretical physics that all the Einsteins and the Hawkings of the world have proposed is actually observed in the real world, right? Because a lot of theoretical physics is theory, right? Until someone observes them in practice, they might very well be incorrect, right? So particle physics is one of probably the most foremost of scientific disciplines when it comes to generating big data. And even 15 years back, 20 years back, they were talking about a petabyte of data being generated, right? How many of you guys have dealt with a petabyte of data? Terabyte is commonplace. Most of you guys have machines that have a few terabytes, if not more, of data, right? But think about a petabyte, and think about a petabyte a decade back, not today, right? So again, for dealing with such large data and processing the data, it's not just idle content that's sitting that someone is just viewing a movie or something like that, but it's actually something that you have to process and figure out the trajectories of these various particles and find out what their properties are and do interesting science, right? And these can have potential breakthroughs and potentially get Nobel Prize worthy stuff done, right? Another big source of such large-scale scientific data is these astronomy sky surveys, where you have these, what you see in the top right is a big telescope with a gigapixel camera that continuously scans the sky every night, right? So you guys might have thought about telescopes and observatories and said, okay, someone's going to be sitting there at the middle of the night and looking through the telescope and making notes and all those things. But nowadays it's for the past 10 years or so, things are much more advanced, right? You can literally sit remotely in your desk and control the telescope and the camera. And better still, you don't even need to do that. The telescope will scan the sky completely. It's like taking a picture of the sky in a continuous fashion at a very high resolution. So next morning you can come back and see how the sky was last night, right? Did I see a meteor fly past? You don't have to do it sitting in the cold, dark tower out there, right? So that means that you're collecting a lot of gigapixel images which have to be processed so that you can figure out how the sky looks like, what are the things in motion, what are sort of the various shifts that are happening. And these can again generate terabytes and petabytes of data and potentially billions of objects, right? So just to wrap up, maybe enterprises, we all know this as well. So you have got Online retail, like e-commerce sites, Flipkart, Amazon, and so on, they're all collecting a lot of data about your purchase history, about various transactions, about what you buy, what your friends buy, and so on. Fintech is another big source of data where they have a lot of history of the transactions, where they might want to understand things like credit card fraud and such, based on the purchasing patterns. Government source of data as well, right? So, how many of you don't have an Aadhaar number? Everyone does, right? So, you're literally mandated, whether you like it or not, to get an Aadhaar number, right? And if you look at this plot on the top left, you'll see that there are about, this is from about I think a week back or so, you have about 1.25 billion Aadhaar numbers issued, right? And they are still continuing to enroll. What you see in the bar plot is actually the number of enrollments on a monthly basis. And that number of enrollments on a monthly basis is more than 1 million, right? So which means this 1.25 billion is continuing to grow just because we produce so many babies every month, right? And they sort of grow older and they get an Aadhaar number and so on. That's a continuous pipeline you're going to have, right? But what's more interesting is on the right side, you are actually looking at how this data is being used for people doing authentication, for doing your KYC if you want to do your by a mobile phone, right? Or going to a bank and opening a new account, right? Or going to the maybe the PDS or the ration shop and buying sort of provisions or so on, right? All of these have authentication based on your Aadhaar number, based on your biometrics and so on happening behind the scenes. So all of these are transactions. And where do you think these transactions are operating? Sitting in a data center, right? So it might be a sort of point of sale device that you might have where you give your biometric or enter your number, but behind the scenes it goes and hits a database sitting in the cloud. And that is logged and that is kept track of when you want to do analysis on top of that, because you might want to, let's say, check for maybe sort of spoofing of identities or check for pilfering of goods and so on, right? Likewise, GSTN is another big source of data that's come online in the last couple of years. Here, where most business transactions and purchases have to go through these e-way bills and invoices and so on. That again, you're looking at about 50 million records or 50 million invoices and e-way bills that are generated on a monthly basis. So that's again a huge source of data, and it's a huge source of data that is actively analyzed, right? Because if you guys have been reading the news, we are the Indian government is in a bad state financially. Targets for collecting money, we are spending much more than we are collecting in taxes, and which means that that's the time when government wants to start taxes and so on. And one easy way to do it is go look at this data and see people who are not paying taxes for goods that they are selling, buying, right? So, in fact, according to news articles, the last income by almost 10%, just because they went in and did data analysis and found out people who are trying to evade the system and got the tax data, right? So broadly, big data is pervasive. It might be as innocuous as reading a news article or a fake news article or Wikipedia. All of these are large corpuses of data. Or it might be using social media to sort of instigate democratic revolutions around the world. So there's a lot of things that you can do with big data by processing it, by sharing it, and so on. So the question becomes, again, this I'm going to skip past this. This is a very philosophical debate. Maybe we can have this over lunchtime, whether big data is good or bad. So I would be interested in hearing your thoughts as well. But maybe I'll play this particular video. We had put this together for a course that I teach this semester. How many of you have seen this video before? Some of you. How many of you have seen this person before? Okay. How many of you don't know who this person is? Ask your friend if you don't, right? You don't have to raise your hand, right? So, now I don't want to put you guys on a spot, right? But if you don't know, just ask your friend, right? I'm going to play this. I don't know if the audio is going to come out properly, but let's give it a shot, right?
Wish I could tell you that we're going to be able to stop all interference, but that just wouldn't be realistic. There will always be bad actors in the world, and we can't prevent all governments from all interference. But we can make it harder. We can make it much harder. And that's what we're going to focus on doing. So today, I want to share the steps that we're taking to protect election integrity and make sure that Facebook is a force for good in democracy.
So this was Mark Zuckerberg, the founder and CEO of Facebook, talking about steps that Facebook was taking in order to prevent election fraud, which is a big issue in the last US elections, where they found a lot of bots were trying to sort of skew the election one way or the other. And Facebook was blamed for not doing enough to protect, to prevent people from being sort of misled by such fake information, right? So there's a video clip of him doing that. And now here's a video clip of him doing something else altogether, or saying something else altogether.
I wish I could keep telling you that our mission in life is connecting people, but it isn't. Behaviors. Spectre showed me how to manipulate you into sharing intimate data about yourself and all those you love for free. The more you express yourself, the more we own you.
Okay, so did we catch him in a candid moment, right? Speaking honestly on camera. So what do you see over here? So if you know what's on the right, so what is it on the right? It's a deep fake, right? So for those who haven't heard of deep fake, it's essentially a way by which you look at.
Telling you that our mission in life is connecting people. There will always
We
be
have
bad
him
actors
keep
in
quiet.
the world.
So deepfakes are essentially looking at a lot of prior video data about a person, video and audio data, and trying to literally build a deep learning model out of that, right? And trying to create sort of artificial or synthetic videos and audios that behave as if it's the original person, right? And these things are getting relatively easy to sort of put together, especially for popular figures with a lot of video and audio data available. And they're also getting more trickier to identify whether it's a fake or not, right? So this is going to be a big challenge going forward. And again, the ability to do this, the techniques that are developed in order to do this are fabulous, right? Like things like deep learning and so on, and computer vision and so on are helping you do this. But it's also the access to data, right? The fact that you have a lot of this video data that's available that you can process using these techniques that makes it possible. And it's also the fact that you can get computing on the cloud and off the cloud at a much more cheaper and affordable rate that makes it possible. So it's it's a perfect storm of data availability, newer techniques to analyze the data, and the computing systems that can allow you to run these models on the large data at large scale that are coming together to make both good and bad things happen, right? So moving forward, right? So some of the key challenges with big data, just to put a specific characteristics or specific features to the data. This is a common metric for checking if data is quote unquote big data or not. Right? This idea has been around for almost like 20 years, but it got popular in the last 10 years or so. And these are called the 3 V's or 4 V's, the letter V's of big data. And this slide coincidentally is from IBM, where they were sort of pitching the challenges of big data. And one of these dimensions is just the sheer size or the sheer volume of data, right? If your data is getting into multiple terabytes, right, or getting into petabytes in size, that's something that a traditional server or a traditional workstation or a traditional software system would be unable to handle, right? So it's going to sort of not be able to process it on time or manage it efficiently and so on. Another sort of characteristic of data that makes it challenging, makes it big data, is if the data is coming in at a very fast rate, right? And you have to process the data and get some interesting observations out of that in a very short period of time, right? So because after that, the data might very well be useless, right? It's examples of these might be your credit card or a net banking transactions, or your UPI or Paytm transactions, right? So if you go to a shop and you sort of do your Paytm payment and it takes 2 minutes for it to happen, will you be using Paytm? Right? You'd rather pay cash and move on, right? If you swipe your credit card and it took like 3 minutes for it to get approved, you wouldn't be using credit cards, right? So all these things have to happen within a few seconds or a few milliseconds. And as Amit mentioned on Sunday, oftentimes some of these credit card transactions probably hit a mainframe system sitting in the backend, because these mainframe systems have been around for a long time. They're extremely reliable. They're fairly sort of customized hardware, but they do what they're designed to do really, really well and really, really fast. But if you take the likes of more recent fintech companies like Paytm and Google Pay and so on, they're not sitting on top of mainframes, right? These credit card companies are sitting on mainframes because they've been around for 30 years. And 30 years back, the only large machine they had was not a cloud, but a mainframe, right? And once you sort of start building your software, right, which has to be extremely reliable, because you can't have transactions be incorrect or not reconciled and so on. And they built these software 30 years back, and they grew larger and larger on these mainframes, more and more complex. And they got to a point where it was too big to fail, as the phrase goes, right? So the software is too complicated, the hardware is too complicated. You can't migrate to a more simple sort of or easier to use like the cloud, because things are too complex. But the new generation of companies, fintech companies, they go to the cloud on day one, right? So they start off with a cloud native application, and they scale as well, right? So though the problems are similar, the solutions are literally decades apart, all the way from a mainframe to your current generation cloud, can both be used to solve the same challenge of high velocity, highly reliable operations, right? And even things like Twitter, right? So they deal with thousands of per second, and they have to analyze these tweets in real so that they can give you the top trending tweets or sort of notifications and so on, right? That's another example of high velocity data. And even things like your share markets, where you're doing trading, has to happen within orders of milliseconds as well, right? And you're dealing with billions of transactions over there, right? A third dimension, which if present could cause data to be big data, is one of variety. And this gets into the whole notion of unstructured data. It's not just sort of nicely laid out relational schemas or tuples that you're getting, but you have a lot of data, media data, natural human language data, whether it's in audio or in text, and it's also semi-structured data, such as social networks, right? So where you have more of a linked data nature to it, which is not like a tabular form, but it's a bit more of a different kind of structure, not just a rectangular structure. So those are again challenges, because traditional systems like databases and so on are not designed to deal with it. And lastly, there are other, besides these three common V's, there are other fourth and fifth and sixth V's that people use as well. Veracity is one of them, and that goes into the trustworthiness of data, right? So the whole idea around fake news right now is very sort of popular or infamous. But you can have veracity challenges even in things like the identity of a person, right? So you have multiple password-based authentication, OTP-based authentication, biometric authentication, and so on, to sort of whoever says who they are is who they are. It might be benign things like, let's say you want to purchase. Let's say I go out there and say, hey, I have a lot of profile data from 40 students from across India, right? I've collected that. I've put in a lot of effort into collecting that. Now I want to sell it, right? So there might be bias for that. There might be targeted marketers who want to go and sell some particular product to some particular person from some particular region who are in the age group of 18 to 25 and who are interested in cloud computing, right? So there are people who buy such things, data brokers and so on. But how do they know that I have access to the data, right? How do they know that I have access to real data, right? And it's not something I just cooked up and I'm giving it. So trustworthiness is a big challenge, and this becomes more problematic if you're dealing with a lot of data and you're doing mission stuff based on the data. Medicine is a great example, right? So you're making diagnosis based on a lot of data that's been collected maybe at different hospitals, right? Saying that, hey, if you have so-and-so combination of symptoms, you have so-and-so illness. But let's say a large chunk of the data was either misdiagnosis or poor handwriting by doctor and it got incorrectly typed in and so on. And you start building your machine learning models on top of that. you're going to come up with wrong diagnosis, right? So here again, things like data veracity or trustworthiness or uncertainty in become. Right? All right, so we've talked about where big data comes from, right? How it might be used in various domains. What are some of the characteristics of data that make them challenging to use and process? Now let's start putting them down into sort of something that's much more concrete, right? Beyond all these fuzzy things and the examples and so on. So typically, if you look at data analysis, right? So it goes through a certain cycle. Typically, you go out and get the data, and this could be from either online websites that are where the data is available. It might be some instruments that you deploy and start collecting the data. It might be sort of transactions or portals that you might have where transactions are happening and so on. So you get all this data, or it could be from surveys that you conduct and so on. And then you start defining sort of questions that you want to answer, saying that, hey, I want to find out what is going to be, let's say, the projected income of this particular age group in the next 5 years, so that I can decide if I want to sell them some financial products, right? So you start defining analytics on top of that. You start defining questions, hypotheses on top of that, and then you define analytics that can help you answer that hypothesis in one way or the other, right? So you start defining these, and then once you've done maybe this analysis on small scale data, you might want to say that, hey, this works for, let's say, a class size of 40. Let's say I want to do this kind of a trend analysis for the entire IISc campus, right? Or I want to do this for all students at all IITs and IISc, right? I want to do this for all students under the UGC umbrella, right? I could sort of scale up my problem dramatically, right? Now, that requires three things. You need to be able to acquire all the data. You need to be able to ensure that your analytics that you have defined that works well for 50 students, works equally well for 5 lakh students. And you need to make sure that the hardware system and the software system you're running on top of can process such large data. So what works on a small piece of Python code on your laptop for 50 students might not work for 5 lakh students if the analytics becomes very complex and doesn't fit in your machine, or the compute time is too much and so on, right? So you need to acquire, analyze, and scale the problem. And when it comes to the scale, is where some of these, you're going to tie your hardware system, your data with your underlying computing platform, right? So I don't know if this, you got a sort of preview of the history of cloud computing in any of the other lectures. But if you look at the growth pattern for the core computing building block, right, which is your, right? So that's sort of what does all your computing, right? If you look at how it's evolved over the last 40 years or so, what you see on the x-axis is time, and what you see in the y-axis are various metrics for a particular processor, for a processor generation, right? And the various metrics you see over here are the frequency, the number of transistors, and the number of cores. So let's focus on these three, right? So how many of you have heard of Moore's law? Again, I can ask the inverse question, but if you don't know, ask your friends. But at the high level, Moore's law is essentially, it's not really a law, it's essentially a prediction or a hypothesis from Moore, who's one of the Intel co-founders, who said that based on his observation of the chip industry and his observation of the advances in physics and materials and so on, he essentially said the number of transistors, which are really the sort of atomic building blocks for your processor even today, so the number of transistors are going to double every 3 years, right? And if something doubles over linear time, it's effectively an exponential growth, right? And that essentially meant that you're going to see an exponential growth in computing performance across time, right? And that actually held up for almost 30 years, right? So if you have something that's just a guess, that's not proven, and that guess holds for 30 years for something as complex as the CPU or processing CPU industry, that's really an amazing guess, right? But things started to fall apart in the sort of mid 2000s, where you started hitting the laws of physics, right? Because transistors, your chip size doesn't grow, You still have, it's almost like maybe a smaller than a credit card, right? Or smaller than your business card. And that's not going to keep increasing. So the transistors have to keep getting smaller, right? And they got to such a small size that you literally had electrons leak from the circuits, right? So things actually started bleeding out, and which meant that your entire circuit has gone for a toss, right? Your computations are no longer valid anymore, right? So that meant that your transistors couldn't get any smaller. So that meant you had to scale out, and when you started scaling out, they started having more and more cores, right? So rather than having a single core or single large circuit that keeps expanding, they split it into smaller circuits. Each of them semi-independently could behave like an independent processor, but cumulatively they could sort of keep growing. By adding more and more cores, you could actually keep staying on that exponential curve, right? So as you see over here, the number of transistors has continued to grow, even though the speed per transistor, right, which is the speed at which the processor runs, that was growing exponentially as well for 30 years, but that started flattening out, right? Because beyond a certain point, you can't bump up the speed without sort of violating the laws of physics, without sort of having leakages and so on. So the speed flattens out, the transistors keep growing, and the number of cores keep growing, right? Which means you still have an increase in your performance, except that earlier you were having an increase both in the number of transistors as well as the speed at which the transistors were running. But now you are limited more to the increase in the transistors, not necessarily the increase in the speed at which they are operating, right? So that's flattened out, right? The other thing that started to flatten out is also the power consumed by these processors, right? Because the higher the wattage of the processors, the hotter they're going to run, and the more chances circuits will start leaking, and you're going to sort of have you're going to go beyond the operating parameters of the processor, right? So what this meant was free lunch that people were having for 30 years was over, right? When I say free lunch, I mean that whenever, 15, 20 years back, whenever you brought out a new version of a software, right? Even though the software is much more complex than the previous version of the software, you knew that the hardware was growing at a much faster rate, right? So the hardware speed was growing faster than the software complexity, right? Which meant that you don't have to spend time writing efficient software. Even if you wrote inefficient software, people will still feel that it's running fast because the hardware is running faster. But then once you started hitting these limits of frequency, so you're not getting that big jump in the CPU speed, just more cores. This meant that your software had to make use of multiple cores that are there, right? That's where parallel computing, multi-threading, and so on start playing a very critical role, right? So you can't afford to just write a single-threaded program, because a single-threaded program can only use a single core, and a single core might just be 1/4 or 1/8 of your processor, which means the remaining cores are being idle, right? So which means if you really want your software to make use of the computing power available, you have to start writing multi-threaded core, multiprocessing applications, and so on, right? And you can as well, right? It's not just using a single machine. With the era of cloud around us for the last decade or so, you have access to multiple machines as well. You have machines with more cores, you got mini machines. So you have to start making use of these multiple machines in a coordinated manner, right? And if you thought writing complex applications for a single-threaded processor was difficult, doing it for multi-threaded is more difficult, and doing it for distributed systems is way more difficult, right? So this means that you need assistance, you need help to ensure that you can still write software that's programmable, that's easy to design, easy to program, easy to develop, and so on, right? How many of you guys regularly program in assembly language? Not have you programmed in, of course. Do you regularly program? Right? Some of you, great. So what do you program in? Great. So out of 40 or so, 1%, right? So how many of you program in Java or C or C++ or Python, right? That's pretty much the entire class, right? And what's the difference between these two, right? So they're poles apart, right? So if you had to write hello world in assembly, that's probably going to take a lot of assembly instructions, right? So that you have to interface with, right? You have to write hello world in Java or Python or C or whatever it is. It's probably a couple of lines of code, right? And what has the higher level language done? It's essentially taken things that were very complicated to write, the actual instructions that get executed in the processor, and had multiple layers of abstraction on top of that, so that behind the scenes you have the compiler, right, that takes your code and converts your high level code into low level instructions, thousands of lines of assembly instructions for maybe a single line of your high level language, right? So that means that you don't have to think about all those fine grained details. You can afford to stay at a high level, right? So just as a compiler in your traditional machine takes a high level language and compiles it to assembly, so what some of these application platforms allow you to do is design your application, right, in a high level language. And this might be a higher level language than just calling it Python or Java, right? It's the next level of like abstraction, right? And once you write it in that particular language, behind the scenes it'll get compiled, if you want to think of it in that way, to run on either many processors or run it on many systems and so on, right? So it's going to sort of do the translation for you, right? But just like you have, there are some things that you can do much more efficiently in assembly language, right? Compared to writing a high level language, and even though compilers are really, really smart, they can only go so far, right? So you could always sort of have an application that a really good assembly coder could write way more efficiently than a really good C or C++ coder, right? Because you are at a much lower granularity. But it's much easier to write that same C code, even though it might be 10 or 20% less efficient, right? So likewise, when you look at all these distributed programming models and platforms, they are not really the most, it's not trying to squeeze out the most performance. You're trying to see how quickly you can go from an idea to a working distributed application that can use, let's say, multiple machines, right? Rather than developing everything from scratch, right? So again, you know about cloud computing. I'm going to skip but broadly, what we are talking about when we talk about cloud computing from the perspective of these applications, we are essentially looking at cloud as a collection of distributed computing systems that are going to work cohesively, right, in order to solve some problem, right? So how do you make all these virtual machines that you're going to rent on the cloud work as if it's a single computer, right? So that if you run something, run your analytic for 50 students on a single VM, you could rent 9 more VMs and scale it up to 500, right? Or 5,000 or 50,000, right? So you just need to add more computing, and the platform will automatically take care of making use of the additional computing resources to solve the same problem without a loss in performance and without a loss in coding productivity as well, right? And here's where distributed systems come into play. How can you effectively make use of multiple machines? And when you talk about distributed systems as opposed to high performance computing, we talk about multiple machines that might be virtual machines, that might be containers, that might be just commodity hardware, not a high-end supercomputer that you might have access to, like the machine on the ground floor. So let me briefly talk about this, because I think we had a question on scalability on day one, if I remember, right? So I sort of didn't quite address it adequately. So one concept that's useful to understand, and this sort of goes to the fundamentals of scalability, is something called strong scaling and weak scaling, right? So scalability broadly is the idea that if you have more machines, right, some performance metric should improve, right? And when we talk about strong scaling, what we say is that as the number of machines increase, if you are solving a problem, let's say for 50 students, right, the time taken to solve that problem will actually keep reducing as you increase the number of machines, right? So if 50 students could be processed in 10 seconds on one machine, if you have 2 machines, I can process the same 50 students analysis on top of that in 5 seconds. At 10 machines, I could potentially do it in 1 second. If I had 100 machines, I could probably do it in 100 milliseconds, right? And so on, right? That's ideal, what's called strong scaling. Strong scaling means your problem size remains constant, the number of machines increase, and the time taken proportionally reduces as well, right? And when we talk about another form of scaling called weak scaling, right? Here the idea is that you still have the size of the machine increase. The problem size also increases correspondingly, right? So which means that if you can analyze data about 50 students on one machine in 10 seconds, you can process twice that number of students, 100 students on machines in the same 10 seconds, right? Or you can do 500 students on 10 machines again in 10 seconds, right? Which means your problem size grows, the number of machines grows, and the time taken remains constant, right? While in strong scaling, the problem size is constant, number of machines grow, the time taken reduces, right? So that's the distinction, right? And they might seem like from an equation perspective, they both seem equivalent, right? So if you just fit in an equation, you'll say that, well, they're both sort of equivalent equations, right? But there's a fundamental difference in what is achievable depending on the type of machine that you have, right? So strong scaling is much more harder to achieve, right? And on their software and your libraries or so on are so well engineered that as you increase the number of machines, they can make use of all those machines really, really efficiently to solve the same problem much more quicker, right? Take a simple example, right? So if you had to solve, if you had to do a project and you had to do it individually, it's going to take some effort, right? Maybe it takes a week for you to solve it. If you had a team of 2, you might be able to solve it faster, right? If you had a team of 3, maybe faster still. Let's say you had a team of 100. Do you think you can solve it in a few seconds? Do you think you can even solve it in a week? It's probably going to take you longer than a week just to figure out who's responsible for what and what the dependencies are and so on, right? That's really the example when we talk about strong scaling, right? As you keep increasing the number of people doing a single task, you are not going to get better returns. At some point in time, it's actually going to be slower to add more people working on the problem because the coordination cost is so much more costly as compared to fewer people solving the same problem, right? On the other hand, let's say one person was doing one project and took a week. 2 people, 2 different projects, you could do it in a week, right? 10 people, 10 projects, same week. That's what we do with homeworks in our class, right? So 50 students, 50 homeworks done independently, you get the same 1 week deadline, right? So that's the difference between strong scaling and weak scaling. Even in real life, strong scaling is very difficult. Same with processors as well, which is why when you talk about distributed systems, when you talk about big data, when you talk about cloud computing, what we are doing is we are emphasizing weak scaling, right? So you can add more virtual machines, you can add more computing resources and solve larger problems the same amount of time rather than solving the same problem in much lower time, okay? So let me pause over here. We are at 10:30, so we'll take a break maybe for 20 minutes or so, okay? Thank you.